are going to be, oh, there we go. Okay. We're going to be talking about section 10.3. And so what we're going to do in this section is we are going to learn about the F test. And the F test helps us determine whether or not our population variances are equal. So you probably remember from section 8.2, we were using the t-test to test for the difference between our two population means on whether or not our population variances were equal. So we had those two different formulas that we had to use. So what the F distribution is, we have S sub 1 squared and S sub 2 squared is representing our population variances, or our sample variances for our two different populations, okay? So if both of the populations are normal, then the population variances represented by our sigma are equal, okay? So the formula that we're going to use to test this, to find our F statistic, is represented here. So essentially, we're going to be dividing the variance of one of the samples by the variance of the other sample, okay? So we have a couple of new things that we're going to talk about with this. So the F distribution is a family of curves, just like our T distribution is. And we have two different degrees of freedom now that we're going to focus on. The degree N is referring to our numerator, and the degrees of freedom sub D is going to be referring to the denominator. All of our F distributions are positively skewed. That means the majority of the data is going to lie on the left side, and the area under the curve is going to equal 1. So let me show you what it looks like. So here we have our family of curves, and our F values are always going to be greater than or equal to 0. And the mean value of our F is approximately equal to 1. Okay, so how do we find a critical value? The first thing that you need to look at is what level of significance you're talking about. That's your alpha. Find your degrees of freedom of your numerator and denominator. And then you're going to use table 7 in appendix B. This is on pages A21 to 24. Okay. So if you're doing one-tailed, you don't have to do anything with your alpha, but if you're doing two-tailed, what you need to do is you need to take your alpha value, cut it in half, and then use that corresponding alpha level on your F table, okay? So I'll show you what I mean by that in a second. We're going to do two examples. Okay, so for this one, we are doing alpha level of 0.1. It's right-tailed, so that means it's just a single-tailed test. Our degrees of freedom of our numerator is 5, and our denominator is 28. So what you're going to do for this is you're going to go to your appendix, and what's going to happen with your F distribution is in the chart, it's a big chart, okay? You're going to find the one that has the alpha level of 0.10, and that's actually the last one on page 824. And you're going to see it says degrees of freedom of the numerator across the top. And so our numerator was 5, okay? So you're going to go over to 5, and then you're going to go down to the corresponding row that has 28 for the denominator. You see that on the left side. And if you do that, you're going to see that the value is 2.06. Okay. So in essence, I know it's going to be hard for you to see because of the camera setup that I have, but you're going over and then down, okay? So over with numerator and then down for denominator. Okay, so let's do another one. Okay, so this one is a two-tailed test. So remember, when we're doing our two-tailed test, you need to cut your alpha level in half. Okay. All right, so that is going to give me 0.025. So I'm going to use the F table that has an alpha of 0.025. So again, I'm going to go over to 4 and then down to 8. And when I do that, I'm going to get 5.0. Okay. All right, so let's do a few other things before we run through an entire example where we test a claim. So in order to perform this test, our samples have to be randomly selected, independent, and have normal distribution. Okay, so nothing really new with that. So our formula is here. And one of the things I want to draw to your attention is the S1 is always determined by the fact that it's the bigger variance, okay? So that helps us figure out which one is in the numerator, okay? And then from there, we can find our degrees of freedom of both the numerator and the denominator. All right, so first we verify that the samples are random, independent, and normal distributions. We state our null and our alternative, specify the level of significance that we're using. Identify your degrees of freedom. Remember the variance, the greater variance determines which one is N1. Use the table to determine your critical value, find your rejection region, and then go ahead and find the test statistic, and you're going to determine if it's in the rejection region or not, and then interpret with our summarizing sentence. Okay, so let's go ahead and go through, I've got 2 examples for you. And I'm also going to make a second video to show you how to do this in the calculator as well. Okay, so we have a restaurant manager and he's designing a system to decrease the variance of time customers wait before their meals are served. Under the old system, a random sample of 10 customers had a variance of 400. Under the new system, a random sample of 21 customers had a variance of 256. At the alpha level of 0.10, is there enough evidence to convince the manager to switch to the new system? Assume your populations are both normally distributed. Okay, so the first thing that I want to draw your attention to is the fact that 400 is greater than 256, right? So that is telling me that, so therefore, S1, so the variance 1 is 400, and that also means that N1 is 10. And S2, that variance is 256 because it's smaller. And so therefore, N2 is 21. Okay. So we're trying to determine if the new system is faster. Okay. So in relation to how I have the population variance for number 1, which is the old system, and number 2, which is the new system, we're trying to see if the new system is faster. So that would mean the variance for the old system is greater. Okay. So this is my null and my claim, my alternative and my claim. Okay. And so then my null would be less than or equal to. Okay, so from here, we're going to go ahead and find our critical value. Okay, so for our alpha level, we have 0.10, and this is a single tail test. Okay, so that means I can just use the chart straight away that has 0.10. And so my degrees of freedom of my numerator is n1 minus 1, which is 10 minus 1, or 9. And the degrees of freedom of the denominator is n2 minus 1, which is 21 minus 1, or 20. Okay, so if I go to the back of the book and I look up the degrees of freedom on the alpha 10% chart, that corresponds to 9 in the numerator and 10 in the denominator, I'm going to get a critical value of 1.96. Okay, so what is that telling me? That is telling me that my rejection region is anything greater than 1.96. All right, so now let's go ahead and do the test. So our formula is so we're going to essentially be doing 400 divided by 256. That's going to give me approximately 1.56. So is that in my rejection region? No, so we're going to fail to reject. Okay, so what does that mean? My summarizing sentence. Let me go ahead and give myself a little bit more room to write this. Okay, so there is not enough evidence at the 10% significance, that's all right, level to support the claim that the new system has less variance than the old system. Okay, so we got one more example that we're going to run through. Okay, so we want to purchase stock in a company, and we're deciding between two different stocks. Stock has a risk associated with standard deviation of its daily closing prices. So we're randomly selecting samples of daily closing prices for each stock to obtain our results. So we are doing this at the alpha level of 5%, and we want to see if one of the stocks is riskier. And it says assume the stock prices are normally distributed. Okay, so the first thing that I need you to notice is that I already labeled it here for you, but 5.7 is greater than 3.5. So that gives me the fact that this is 1, and so stock B is 1 and stock A is 2. Okay, so then the other thing that we're going to find is we are going to find our variances. So to do that, we're going to square these two values. Okay, so I'm going to say S2 squared. So we're just going to do 3.5 squared, which is 12.25, and 5.7 squared, which is 32.49. Okay, so now that we have that, let's go ahead and state our claim and then identify our null and our alternative. So in this case, since the claim is wanting us to test whether or not one is riskier, we are trying to see if the population variances are not equal. Okay, so we're trying to see if our population variances are not equal. So is this my null or is this my alternative? And the answer is it's my alternative, which means my null is that they're equal. Okay. So since this is a two-tailed test, that means my alpha level needs to be cut in half when I'm looking at my chart. So I'm going to cut 0.05 in half, and that's going to give me 0.025. Okay. My degrees of freedom of my numerator is going to be 30. And my degrees of freedom of my denominator is going to be 29. All right, so let's go ahead and find our critical value using the 0.025 and the fact I have a numerator degrees of freedom of 30 and denominator of 29. That is going to give me a critical value of 2.09. So we're rejecting everything that is greater than 2.09. Okay, so now let's find our test statistic. So to do that, we're going to divide our two variances. So 32.49 divided by 12.25. And if I do that, I'm going to get 2.65. All right, so is that in my rejection region? It is. It's here. So what does that mean? We're going to reject the null. Okay, so let's write our sentence. There is enough evidence that the 5% significance level to support the claim that one stock is a riskier investment. Okay, so I'm going to post a second video of me showing you how to do this in the calculator, okay? So make sure you watch that as well.